Okay, here's one more key concept video where previously we talked about the dot product between two vectors. Now we're going to talk about cross product between two vectors. And as noted in the lecture, key thing to remember about the dot product is that you end up with a number. With the cross product, we end up with a vector. So this is sometimes called the vector product. Cross product and the vector product are the same thing. Okay. Now, the definition of the cross product, so A cross B, is given by the magnitude of A times the magnitude of B times the sine of the angle in between them. And I wanted to give you a kind of intuition about what this means and kind of sketch this out geometrically for you. So this is the definition that we're given, and what we did in the notes was we stated this is the size of the vector, is this A times B, magnitude of A times magnitude of B times sine theta. The orientation of this vector is that it is orthogonal to both A and B, or to the plane containing A and B. And the direction of that vector is computed with what we call the right-hand rule. So what this actually looks like in practice is if you imagine we have two vectors, A and B, which are, I'm just going to draw them as orthogonal to each other. So you can sort of imagine that this is a sort of plane that contains A and B here. The vector C will be in this direction. So it's orthogonal to both B. So I'm not sure I can draw this effectively, but orthogonal to both B and A. Okay. And in this case, because I've drawn A and B as at right angles to each other, it's fairly easy to see that C should be up here. But of course, any vector that I draw in this plane, so here's another one, B prime, say, that's also in this plane. So C would be in the same direction. So how can we get some sort of intuition about this this vector then? Well, if we take the simple case that A and B are orthogonal to each other to begin with, well, that means that the angle in between them, this theta here, is 90, and sine of 90 is just equal to 1. So the magnitude of this vector, C, the cross product between A and B, will just be equal to the magnitude of A times the magnitude of B. And as it turns out, that's just the area of this square. Okay, I know it looks like a parallelogram, but that's because we're kind of trying to draw 3 dimensions on this 2-dimensional page here. So the area of A and B, of this square defined by A and B, then determines the size of this vector C. So if we were to take another pair of vectors that weren't orthogonal to each other, so A and B here, well, C would still be in this upward direction. But now this theta here is much smaller than 90, and so sine of that angle will be smaller than 1. And actually the area which is relevant here is the area of this. Now this is a parallelogram, okay? But that area is now smaller than the area of this square. And this is kind of the maximal case. So this is the largest area that we could define with these two vectors. And you can see that this is some sort of intermediate case. In the case where A and B are actually aligned with each other, so if I have A and B both in that direction, well, then the angle between them is 0. And actually then C doesn't, has no magnitude. Okay, so the magnitude of C is 0, and so we don't get a cross product there, or cross product is identically 0. So that's the kind of minimal case where the angle is 0. Maximal case when the angle is 90 degrees. Some intermediate case when it's theta like this. And just to say as well, we didn't really go over this in the lecture, but this designates the right-hand rule. So if you imagine we were sitting underneath, so if we were kind of underneath this plane looking up, and we were looking at A and B, you can imagine that kind of rotating from A to B would be in the clockwise direction. You can imagine that if we're kind of looking up. And the clockwise direction then kind of defines the direction of C. So we call this the right-hand screw rule. If we had a screwdriver and we turned it from pointing at A to pointing at B, that would push the screw in this upward direction. Okay, B cross A, if we were above and looking down, and we took the cross product between B and A, well, turning from B to A would go the other direction. It would go this direction. And so that would drive the screw in this downwards direction. So B cross A actually is the opposite direction. So that's the right-hand screw rule. But this is the kind of intuition that I want you to build up, is that this somehow relates the kind of area enclosed by these two vectors. And in some senses is a kind of vector which encapsulates how misaligned the vectors are. So if they're at 90 degrees, that's sort of a maximal. We get sine of 90 equals 1. If they're aligned with each other, then we get 0. Okay, and if they're sort of along the same similar sort of direction, but with some angle in between them, we get some smaller vector here, c. So that's the key idea with the cross product.